This is the lecture for chapter 3 of our textbook, Ohm's Law. The topics we cover in this chapter include the current, voltage, the resistance, which are the items that form the formula for the Ohm's Law. Then we'll talk about practical units, multiples and submultiple units, the linear proportion between voltage and current, electric power, power dissipation in resistance, power formulas, choosing a resistor for a circuit, electric shock, open circuit and short circuit troubles. Alright, let's start by defining what Ohm's law formulas are. There are three forms of Ohm's law. There are basically these three different ways of writing the same formula depending on what you're looking for. Ohm's law says that the current is equals to the voltage divided by the resistance. If we solve for voltage on this formula, we get the voltage is equals to the current times the resistance. Or if we need to solve for the resistance, solving from the original formula, then we can say that the resistance is equals to the voltage divided by the current on a resistive circuit. So I is the symbol for current, voltage is a V, and R will be the symbol for the resistors. First, the current. Current is equals to the voltage divided by the resistor or resistance. In practical units, this law may be stated as amperes. So volts divided by ohms give you amperes. Now, depending on which variable you're solving for, then your result will have different units. So if you're looking for the current, then the current will have amperes as units. The volts will be the unit for voltage, and ohms is the unit for resistance. Here is an example of how to apply the Ohm's law. In this first diagram right here, we have the voltage across, from this voltage source, which is connected in parallel with this resistor of 4 ohms. So we want to know what is the current flowing through this resistor. So the current is the voltage divided by the resistance. So 20 divided by 4 equals 5 amps. If we have the resistors and the values of the current, then we can find what's the voltage associated to this source. From the formula right here, the voltage equals the current times the resistance. So we multiply the current times the resistance and we get 12 volts. So now we can say that this battery or this voltage source is a 12 volt source. And if we have the current, if we know the current flowing through the circuit and we know the value of the voltage in this source, then we can find the value of this resistor right here. From here you can see that the resistor equals the voltage divided by the current. So 6 divided by 3 equals 2, and the unit for resistance is ohms. So that would be 2 ohms. Units of voltages. The basic unit for voltage is the volts. Okay, so if we're dealing with large amounts, we might want to use multiples of the volts, like kilovolts, for example, is 1000 volts. Remember from our chapter 1, or the introductory chapter, actually, we were talking about units of 10, powers of 10s. So 1 times 10 to the 3, that's 1 times 1000. So we can substitute the 10 to the 3 by the K for kilo, and that would be kilovolts. If we're talking in the millions, of volts, then instead of saying 1 million volts, we can always replace that with the 10 to the 6th power, and that will be 1 megavolt. In some cases we will see 20 megavolts, 3 megavolts, 5 kilovolts. Anyways, the multiples of the units are for large quantities, large amounts. Sub-multiples units for voltages are millivolts and microvolts. So 1 millivolt is 1,000th part of 1 volt. So instead of writing 0.001 volt, we can always put 1 10 to the minus 3 volts, which is the same as saying 1 millivolt, or 1 times 10 to the minus 6 for microvolts. That's the difference between multiples and submultiples. Okay, multiples are for large amounts like kilo, megas, and submultiples are for very small amounts like millivolts and microvolts. Same for the current. The basic unit for the current is the amperes. For short, we always say amps. Submultiples of the current will be milliamps or microamps. These are the most typical submultiples used in electronics. The resistors or resistance have their units is ohms, and again, so if we have multiples like 1000 ohms, we can replace that with 1 kilo ohm, or let's say for example 20,000 ohms. Instead of writing 20,000, we can always say 20 kilo ohms or 20k ohms. Same for mega ohms, where we are in the millions of ohms. So instead of writing down the 6 zeros for the millions, we just put an M for mega, and we can say 1 mega ohm, 3 mega ohms, 20 mega ohms, and so on. The linear proportion between voltage and current. Ohm's law formula is the current is equals to the voltage divided by the resistor. So there is no exponents here, so we can say that this is a linear equation in which our variables will be the current and the voltage, and 1 over the resistor will be basically the slope of this line. Okay, if it's linear because it passes through 0, and the slope of this line is 1 over the resistor, so we can actually say that this current is equals to 1 over R times V for voltage. As you can see, the current and the voltage are proportional, directly proportional for any one value of R. As R gets bigger, I decreases. And as R gets smaller, so the current increases. Take a look at this circuit right here, for example. This goes from 0 to 12 volts. The resistor is 2 ohms. And what is the current? Here are the values. The volt is 0, then the current is 0, because 0 divided by 2 is still 0. The voltage is 2, the ohm is 2, so the current will be 1. 2 divided by 2 equals 1, 4 divided by 2 equals 2, 6 divided by 2 equals 3, and so on. As you can see, the voltage goes up, the current goes up, because they're directly proportional. So if the voltage is a constant, then the current will decrease as R increases, like I mentioned before. Because R is in the denominator, so the bigger the denominator, the smaller the result. Okay? And the current will increase as the resistance decreases. Here are some examples. If R doubles, I is reduced by half. If R is reduced by 1/4, then the current increases by 4. This is known as the inverse relationship because it's inversely proportional to the resistor. So in other words, the current gets bigger as the resistance gets smaller, or the current gets smaller as the resistance gets bigger. So now linear, there's a couple of different types of resistors. So a linear resistance is a resistance that has a constant value of ohms. Its R does not change with the applied voltage, so V and I are directly proportional. If the resistors are fixed, so they are directly proportional. There are other type of resistors, different types of resistors that are considered linear resistors. Okay, linear resistors means that when you plot the voltages and the amperes for the equations, this is a fixed value. So therefore, what you get is a line. Okay, in this graph, the amps is a function of the current is a function of the voltage. Okay, and the resistor is a fixed value, so this is a linear relationship. As you can see, the bigger the voltage, the bigger the current, and this is a linear relationship, a straight line. That means the resistance is a fixed value. Now, the smaller the resistor, the steeper the slope of this line. Because remember, the formula says I equals 1 over R times D. Meaning that the slope of this line is 1 over R. Okay? So the bigger the slope, the more steep the graph is. So, and this slope of 1 over R gets bigger as the resistance gets smaller. There are also nonlinear resistance, means that the change value, the values change. In a nonlinear resistance, increasing the applied voltage produces more current, but current does not increase in the same proportion as the increased voltage. It means that it will increase, but it will not be like the previous example where we saw that if it increases by 2, then the current increases by 2. If it increases by 3, then the current increases by 3, because they're not linear. This is an example of something that is non-linear. See that this is not a straight line; it's a curve. Okay, so as you can see right here, the current it goes up as the voltage goes up, but they're not proportional. Like from here to here, for example, from 0 to this point right here, see the increase in current was huge, was 4 times the voltage, right? But from here, let's say take this point, from this to here, the voltage went up by 1 unit, the current goes from here to here, not even 1 unit. Okay, if from here for 1 unit of voltage, the current only goes up like almost 1 whole unit. From here to here, the voltage goes up 1 unit, and then the current goes up 4 units. So this is not a linear relationship. This is what they talk about when they mention non-linear resistance, because the resistance also, they change depending on different factors. One of the let's see what I was saying here. The tungsten filament in a light bulb gets hot, its resistance increases. Okay, so when you have a light bulb, this is a resistance right here, the resistor. Okay, But as the harder it gets, the more opposition to the current it has. And it could be up to infinity, because once it breaks, then the resistance from here to here will be basically infinity. Another nonlinear resistance is the thyristor. The thermistor. A thermistor is the resistor whose resistance value changes with its operating temperature. Thermistor, okay, I guess it's coming from the thermal. So this type of resistors change their values. In other words, they have more resistance or less resistance depending on the temperature that they've been exposed to. Now, electric power. The basic unit of powers is watts, is the watt. And multiple units of powers, the kilowatts, the megawatts. These are very common units when it comes to the utility companies. Submultiples, just like the voltage, can be very small amounts of power. There will be milliwatt for 10 to the minus 3, or microwatt for 10 to the minus 6. So this is a 1,000th of a watt, and this is 1,000,000th of a watt. As you may recall from the previous 2 chapters, we read about work and energy. They're basically the same thing with identical units. The power is different. It is the time rate of doing work. In other words, the power is equals to the work divided by time. Or we can also say that the work is equals to the power multiplied by the time. Practical units of power and work. I mentioned before, the power is expressed in watt. Now remember actually we haven't talked about it yet, but powers is equals to the multiplication or the product of voltage and current. So 1 volt from chapter 1, remember, it was 1 joule divided by 1 coulomb. And 1 ampere is 1 coulomb divided by 1 second. So if we multiply the voltage times the amperes times the current, so these are the units that we're going to be dealing with. This is the formula for the power. The power is equals to the voltage times the current. So if the voltage is expressed in joules over coulombs and the current is expressed in these units, when we do this multiplication, this one, the coulombs and the coulomb cancel, and then the power is 1 joule over second. These are the units of power. So these units combined is what is known as watt. Kilowatt hours. The kilowatt hours is the unit commonly used for large amounts of electrical work or energy. For example, the electric bill is calculated in kilowatt hours. So basically, the kilowatt hour is the billing unit. The amount of work can be found by multiplying the power in kilowatts and the time in hours. Let's calculate the cost of electricity as the power company bills you. If you have an air conditioning that operates at 240 volts and 20 amps, so the power consumption of this device will be the voltage times the current. So 240 times 20, that gives you 4,800 watts. This is a typical unit that we can convert into a multiple of watts. Instead of saying 4,800 watts, we can always say it's 4 kilowatts. Let's assume that this air conditioner runs only for half a day, 12 hours. So we multiply the power times the hours of use, and that will give you 4.8 kilowatts times 12 hours, and that will give you 57.6 kilowatt hours. That is what the power company uses to calculate your bill. So for that AC, if the kilowatt hours is cost 8 cents, then you will be paying $4.61 per day for the AC to be on for 12 hours. Power dissipation and resistance. When current flows in a resistance, heat is produced from the friction between the moving free electrons and the atoms obstructing their path. In other words, the current, when the current is flowing through the resistance, heat is generated because of all the movement inside the resistor. So the heat is an evidence that the power is being produced. So, or I should say consume, okay? So power is used during, producing current, when the current goes through a resistor. Power dissipation. So basically, the amount of power dissipated in the resistance may be calculated using any one of the three formulas depending on which factors are known. So if we know the current and the value of the resistor, we can always do that the power equals the current square times R, or V square divided by R, or just simply V times I. Because remember, this is the base formula for power. That's power equals the voltage times the current. From Ohm's law, you remember that the voltage, for example, equals the voltage is equals to the current times the resistor. So if we plug in current times the resistor here for voltage, then we go back to this formula. It will be current times the resistor, which is current squared. And the other one will be, for example, if we know that from Ohm's law, remember that the current is equals to the voltage divided by the resistor. So if we substitute this I by V over R, we get V squared over R, which is this one right here. So all this is basically the same formula using Ohm's law. So there are three basic formulas, like I mentioned before. Okay, we just went over this slide. This is the Ohm's law right here. If you know Ohm's law, you can always plug in the values for different. You can play with this formula and use it according to the elements that you have at hand. Now, combining Ohm's law formula, we get this. All right, same thing that we just went over. We know this is the Ohm's law. We know this is Ohm's law. So if this is the power formula, we can plug in these values, substitute V or substitute I accordingly. We can put this on this, and then we get the different ways of expressing the power. Right. Applying the formula, we have all this right here. We already know the voltage, we have the current, and we have this one. And we want to know what is let's say the power consumed by this resistor. We can always say V times I, 100, or V squared. I squared times R, which is 25 times 4, would be 100, or V squared divided by R, that's 400 divided by 4 is still 100. See, it doesn't matter how you use the formula, you should be able to arrive to the same solution. So when choosing the resistor for a circuit, determine the required resistance value Calculate the power dissipated by the resistor using any of the power formula, and then select the wattage. Select the wattage rating for the resistor. That will provide an adequate quotient between the actual power dissipation and the resistor's power rating. Now, how are we going to choose the elements of our circuits? We're going to become very efficient in that, because once we have more practice on solving problems. But these are the steps. Okay, so the maximum working voltage rating, a resistor's maximum working voltage rating is the maximum voltage a resistor can withstand without internal arcing. Arcing will be damaging the resistor. Okay. The higher the wattage rating of the resistor, the higher the maximum working voltage rating. It's just self-explanatory there. Alright, so if we go back to the formula, of power, remember power equals V squared divided by R, and we solve for V, that would be the maximum voltage that for any resistor, for the resistor. Okay, so you multiply the power times the resistor and then take the square root, because this comes from the formula that power equals V squared divided by R. So you can find out what's the maximum voltage that resistor can handle by solving that formula for the voltage. Okay, electric shock, just be careful. Basically, this is what it tells you. Just be careful, and we're gonna learn all these safety issues during the lab. Okay, the power is something that you cannot play with, so we have to be very careful. You have to be isolated from earth, ground. Open circuit and short circuit troubles. Alright? An open circuit has zero current flow. So in other words, this is the normal circuit. If it breaks, if the resistor breaks, then it's open. There's no current flowing through this. And that's what I mean by open circuit. In other words, this resistance becomes infinite. Okay, so no current can flow through it because it's broken. So the resistance between these 2 points is infinite. And also, a short circuit has excessive current flow as R approaches zero. Okay, the current will be infinite. Let's assume this is a circuit, right? A regular circuit. You have 2 amperes, 10 volts, and the resistor is 5 ohms. If you connect a wire from this point to this point, then this is what we call a short circuit, right? So basically this overtakes this position right here, and now the resistance in the wire, in the ideal wire, is zero. It's almost zero. So the voltage divided by the resistance gives you the current. So divide 10 by 0, that gives you infinity, right? So if you short circuit something, you will get an excessive current flowing through the circuit, and it will damage whatever device are connected to it. Alright, and that marks the end of chapter 3. In this chapter we only covered the basics of Ohm's law, and the upcoming chapters we're going to have more interesting applications for Ohm's law. As always, thank you for your attention and the opportunity to serve you. Until next time.